I would like to invite Johanna Ziegel from ETH Zürich to come up here and start her talk on calibration of probabilistic predictions. And then we will move on through the other calibrations throughout the day. Please, Johanna.
Thank you. It's a great pleasure to be here, and as Todd is introduced, this will be more of a tutorial than a full research talk. I want to talk about what I mean by calibration of probabilistic predictions. And I see that our youngest participant is leaving because it's really a tutorial. So yes, let me jump right in. I'll make clear what I will exactly talk about and what I will not talk about. Please do feel free to interrupt me at any point. Should you have a question, I'm happy to take them throughout the talk so that it's most beneficial for everyone. Okay, so what is the idea? We have some y throughout the talk. Y will be some unknown future outcome. You can think of various things, either temperature tomorrow, 12 in Cambridge, the event of rain tomorrow in London, any rain over the whole area during the entire day somewhere, the default of a credit card client, or maybe the amount of precipitation tomorrow in Cambridge and Oxford. So there we would want two numbers. So here you see that the outcome space for y can be various things. These are all fairly simple examples still, but they are very prominent. A lot of predictions are made that are just for events, for binary outcomes. And of course, a lot are made also for real valued outcomes. If we have just a single valued best guess, you ask like, what do you think is temperature tomorrow in Cambridge at 12? And she says, well, I think it's going to be about 17 degrees. And then tomorrow, it turns out to be 17.7. And we'll be impressed. She was pretty good, right? So we will not say she's wrong just because she didn't hit the point. So somehow we all intuitively associate uncertainty to such a point prediction, to such a best guess. But if we really want to quantify the uncertainty of y, one way we can do this, and that's the way that I will be addressing in this talk, is we can quantify the uncertainty of y by a probabilistic prediction f. So this f would be a distribution over our outcome space. So if we have binary predictions, that's the part that I will consider first. We will just have a probability. If we have real valued predictions, we would have a distribution over the real line. And then it can get, of course, it gets more complicated the more complicated the outcome space. Now, if we have information available that we want to base our prediction on, say x are some covariates, they can be really anything that you want to base your prediction on, from expert opinion to measurements to numerical weather prediction models or anything you like, then our goal should be that this f, that we are the probabilistic prediction, it should approximate somehow the conditional law of y given our information. That, I guess, intuitively makes sense. That would quantify the uncertainty of y given the information we have. Now there are, of course, I want to make a disclaimer at this in the beginning, there are other ways of quantifying the uncertainty of y. We could issue a prediction interval, right? Not a full probabilistic prediction, not a full distribution, but just an interval where we expect y to lie with high probability. We could predict some measure of variability. We don't only predict, let's say, a mean of y, but also a variance or a standard deviation. So there's other ways, but in this talk, I want to focus on full probabilistic predictions. So the goal is I want to discuss quality criteria for probabilistic predictions. So in particular, I want to answer the question, what does it mean for a probabilistic prediction to be calibrated? Okay. Now, one thing that I do not want to get into, that other talks, in particular the next one, will be talking about this, is how do we calibrate predictions? Okay, that's a different question, right? This is in some sense not a constructive talk. It's more of a descriptive talk. I'm asking myself, what are even our goals? What does calibration mean? When do we say something is calibrated? Then, of course, the next question, and in the talk right after, you will see one very popular and influential approach in doing so, is how do we get those? How can we ensure that predictions are calibrated? Okay, just to set the stage of what I want to do, what I don't want to do. A second topic that I want to look at in my talk is how do we compare predictions, and how are such comparisons related to the calibration of predictions. Okay, we can say one is better than the other. Does that mean it's better calibrated? Does it maybe mean something in between, or is it a combination of several things? So that's what I'll do in the last part of my talk. Now, so far we have y, this unknown future quantity. Typically forecasts are sequential, right? They're issued many times over and over again, or many days, or many occasions. But a lot of concepts on calibration are easier to understand if you think of a hypothetical one-period setting where you have a forecaster. How should he best predict that one future outcome? If you then want to do empirical assessment of whether that forecaster was calibrated, of course you need repeated forecast observation pairs. But just to formalize the notion of what would be the best thing to do in one step, it's actually more instructive, I find it's also easier to grasp to focus on a one-period setting. Now, here in the setting we are, y, the future outcome and the forecast, they're both random and defined on some probability space. We're not going to see this probability space much, but just be aware, so y and f are both random quantities. So here is the outline of what I'll cover. We did the introduction. I'll talk about calibration for binary outcomes, for real-valued outcomes, and then very briefly for multivariate outcomes. I'll say a word about calibration and averaging, and then in the second part, I'll talk about proper scoring rules that concerns the comparison of different predictions. Okay, so let's start with the simplest case. We have a binary outcome. So our future random variable, some event that can happen or not, so y can only take the value 0 or 1. So the two examples I gave here were, you could think of the event of rain tomorrow in London, or the default of a credit card client. But of course, there's gazillions of other examples. Now, the distribution of y is characterized by the probability of a success of y. So in order to characterize the full distribution of y, we only need to issue a random variable p that takes values between 0 and 1, that characterizes the distribution of y. Now in this case, the binary case is a bit special. If you think of the distribution of a success given our information, that's the same as the expectation, essentially, of y given the information. So in that special case of binary predictions, predicting the distribution or predicting the mean are the same thing. In both cases, we get the same thing. So that's also why a lot of things are special for binary outcomes, because you can view them either as a full probabilistic prediction, or you can view them as a prediction for a mean. Okay? We will take here the perspective of considering it prediction for the whole distribution, but just that as a disclaimer. Okay, so when do we call such a prediction for a binary outcome calibrated? So we call it calibrated, or oftentimes it's also called reliable, if the probability of success given the predicted probability is the predicted probability. So what does that mean? It follows the idea that predicted probabilities should align with observed frequencies. So let me try to make sense of for you of this formula. So suppose we condition on the prediction. Now, as I said, typically we have lots of, if we want to make sense of this, we have lots of cases of predictions and outcomes. So lots of pairs of a number between 0 and 1, and then a 0 or 1. Now, you fix some number, let's say you fix 0.3, and you collect all times where you predicted roughly 0.3. That means you condition on p, and then you check how many times when you predicted something around 0.3 did you actually observe a 1. And then that empirical frequency of these 1s should be roughly 0.3. Then you're calibrated. And that's exactly what's encoded here formally. Okay, so that would be calibration for binary outcomes. Let me give you a very small simulation example here. Suppose we have, as information, we have two random drivers, x1 and x2. They're both normally distributed. One has a standard normal distribution, the other one has variance 2. They're independent. And the true success probability of y, given this information, is the CDF here, this is the CDF of a standard normal, of x1 plus x2. You just need some map that goes onto 0, 1, right, to construct such an example. And then we have 4 different predictions. The first one predicts 1/2. No matter what the information, constant prediction 1/2. Second one predicts phi of x1 over root 3. Then P2 predicts phi of x2 over root 2. And P3 predicts phi of x1 plus x2. Okay? So the last one has full access to the 2 random drivers in our prediction problem, so that should be somehow the best prediction. Also, we know here it's the true conditional probability, so that's, of course, that's calibrated in the sense we discussed before. But these are as well, right? The P2 is a better prediction than P1 because it has access to the information that's more variable, that would introduce more error if you don't look at it. And all of these are calibrated. Now here I've tried to give you a visual of what this means. These are just 25 IID realizations of this scenario, and the zeros and ones are these dots here. These are the realization, the Ys. The black line is the prediction P0. P1 is the green line. Then P2 is the blue line. And P3 is this turquoise line. So you see visually that P1 is worse than P2, then P3, then P0 is worse than P1, worse than P2, worse than P3. But so far, the only thing, if we look at calibration, they're all calibrated in the sense that I introduced before. Okay, now, how can we assess calibration in applications? So what are diagnostics we have at our hand? These are so-called reliability diagrams. If you want to assess calibration, you need data from predictions and observations, so P1, Y1 to Tn, Yn. And here I plotted it in our simulation experiment. You do essentially the thing that I told you when I explained to you what the definition of calibration means. You collect all predictions, let's say around 0.4, and then you plot the empirical frequency you have observed. Okay? And here these are the plots for the simulation example we saw on the last slide for forecaster 1, 2, and 3. Here you have a histogram of the forecasts that were made. That's just for information, maybe about how much you can trust this line that should be on the diagonal in every forecast case. Here I've given a reference from 2021. Actually, one of the authors, Timo, he's coming to the workshop. Of course, reliability diagrams are way older than this reference. They've been around for very, very long. Why am I giving this reference? This reference has introduced, in my opinion, a very convincing way of how to choose the bins in such reliability diagrams. Because this, it's not trivial at all. It's similar to a problem you encounter in histograms. You can choose the bins in such a way that you can either make this look much more diagonal than it is or much less, depending on where you really put your bin boundaries. And the binning they have introduced is fairly immune to such subjective choices, so I think it's a very good choice. That's why I've given this reference here, but of course, yes, reliability diagrams are way older than this. And of course, you can also then do tests for whether you are on the diagonal, whether you are probabilistically calibrated or not. One popular test in this direction is the Hosmer-Lemeshoff test. I don't want to go too much into this because I think oftentimes it's oftentimes easy to reject that you're calibrated, so in terms of a goodness of fit test, but it doesn't tell you necessarily so much what is your defect. And oftentimes you see that better in such a diagnostic, where you see, for example, that for high, should this here deviate up here, right? You know that you have a problem when you make high predictions, right? So that's often more informative than just the test decision, you're not calibrated. Then you still don't know what's wrong and what to improve. Okay, here's just a quick application example, just that you, for a bit of seeing this, that it's not only theory. So here it's about probability of precipitation forecasts. We have 5 different forecast horizons, so every column corresponds to 1 day ahead, 2 day ahead, 3 day ahead, and so forth predictions. Every row corresponds to a station at an airport, so we have airports in Brussels, Frankfurt, London, and Zurich. And every color now, there's no need for you to distinguish all of them, but you just see that there's lots of colors. Every color here corresponds to a forecasting method, to a way of constructing these probability predictions. And so in this one plot, we're comparing all these different methods in terms of their reliability. You see one that's always down here that's obviously not calibrated. That was the baseline. That's the baseline that then all these methods used as information and tried to improve upon. Most of them did okay in terms of calibration. There is one that's a bit below, that tends to be a bit off. But that's just as a short illustration of how such reliability diagrams then could be used for checks in applications. Okay, so this is the binary case. We could give a very clear definition of what calibration means. And this, I would say that this notion of calibration is also quite universally accepted in the literature. There's not that much debate about what calibration for binary outcomes should look like. There are some weaker notions where you do approximate calibration and things like that, but they all start from this fundamental idea that this type of calibration should hold. Now let me come to real-valued outcomes. Things become a bit more complicated for real-valued outcomes. So here the example that you can think of is temperature tomorrow at 12 in Cambridge. And we want to quantify the uncertainty of y by a probabilistic prediction f. So this probabilistic prediction is a distribution on R, so typically specified as a cumulative distribution function as a CDF. Now again, what I had on my first slide, f should approximate the conditional law of y given x. Now let's see how well f does this and what does well even mean here. So I want to give a few pictures of illustration. Here, this is an illustration of temperature forecasts. Here is temperature, here's the date. And here you see point forecasts, best guesses for temperature, right? So you have over the timeline, the blue line gives you best guesses for temperature 1 day ahead. And then the observations are these orange crosses, where you have one observation per day to see whether your best guess was a good idea. Now, what does this look like if you are in the probabilistic prediction case? Every day, we're predicting a distribution, typically a normal distribution for temperature. That's here depicted as a cartoon, as a box plot. And this distribution changes, of course, every day we make the prediction. And we have one outcome every day to compare it to. Okay, so this would be the probabilistic prediction setup for real-valued outcomes. Here is one application example that goes away from weather forecasting. These were predictions for patients, for the length of stay of patients in intensive care units. So the idea was, can we get a probabilistic prediction for how long is a patient going to stay in the intensive care unit? These times are measured after midnight, the first time they're there, based on covariates they had when they came in. And then we want the distribution of their length of stay, no matter whether they leave because they die or they leave because they're cured. What's the distribution of that length? So then you can better plan how many beds you need and so forth. And here you see 3 different methods that try to accomplish this. You see this for 4 different patients. So for every patient, such a prediction is a CDF here given like this. Okay? And why do they have these wiggles? Some of the method, that's because patients are only dismissed at certain times of the day. That's just due to protocol in the ICU. So that's not a flaw of the method here or anything discrete. That's just really practice. So that's one example where you could have probabilistic predictions for a real-valued outcome. Another example is a very classical one that's from the Bank of England. They give probabilistic predictions for here. This is for unemployment and this is for inflation. These are just pictures of where they did show their predictions into the future in terms of here prediction intervals. But the prediction they give are really 2-piece normal distributions. So it's normal, like a normal distribution that's cut at the mean and has a different variance on 2 sides. That's what they use here for these predictions. So these are really full probabilistic predictions for unemployment and for inflation. Okay, so here is in pictures again, what is the difference between probabilistic and point predictions? We have a forecast. This is either a point or it's a full distribution, here a normal one. We have the same observation, and the verification part is very different now in both cases. Either we compare two numbers, or we compare full distribution to one observation. Okay? Yeah, so how should we do this? I'll try to explain different notions of calibration now here with a bit of cartoon pictures to hopefully make this a bit intuitive. You see 4 panels here. These are 4 different forecasters. In all panels, you see this red and the black line are a bit thicker. That's not because they're special, it's just so that you can you don't get distracted by all the lines and you can see some of them a bit more clearly. The vertical lines are the observations. They're the same for all the 4 forecasters. And the other lines are the predictive densities they issue for the vertical lines. So here for this black observation, this density was issued, and for the red observation, this density was issued. The first forecast, I guess, looks pretty good by the eye. The second forecast, it does something a bit funny. It has this bump here, and it does a bump here. The third forecaster seems to have a sign problem because the prediction for the black line is over here, right? So that's a bit off. And the fourth forecaster, all predictions are on top of each other. So the fourth forecaster may be good or not, but certainly it's uninformative. So the fourth forecaster you can think of as predicting for temperature tomorrow in Cambridge, you're predicting the distribution of temperature over the year in Cambridge. That's certainly calibrated, but it just doesn't tell you very much on how you should dress. Okay, so what do we mean by calibration of such forecasts for real-valued events? So before we said that the predicted probabilities should be in agreement with observed frequencies. Now, if we have predictive distributions for real-valued outcomes, we can derive predicted probabilities for any event that is in relation to this real-valued outcome. Right? So we get lots of probability predictions for lots of events that are in relation with our future y. And all these predicted probabilities, these probabilities derived from the predictive distribution should align with the observed frequencies of the events. Of course, we cannot check this for all events. So somehow we have to come up with notions of calibration that check this simultaneously, that simultaneously make sure that these derived probabilities do have the correct frequencies. Now, what is by far the most popular way of checking calibration for real-valued outcomes? That's looking at so-called probability integral transform values, PIT values. So what you do is here, you have the predictive CDF Fi, and you plug in the observation Yi, and you hope that the random variable that comes out has a standard uniform distribution. You can easily, like graphical checks for this are nice because you can simply plot these values Fi of Yi in a histogram with the known problems with the binning, but essentially you should see a flat histogram. Or you plot it, what I think is preferable, you plot it as a PP plot and you should be on a diagonal, then you don't have the binning problem. But that's just as a side note. Of course here, if this F is not continuous but has some jumps, that's a bit harder to justify, and in fact you should do a bit of randomization when you have that, if F is not continuous. But that's all well established, that's not a problem per se, these things have been studied there, it's clear what to do. I just didn't put it here to have a bit more of a clean notation. Now, this type of calibration is very closely related to the validity of conformal predictive systems, and we'll hear more about this, I suspect, in the next talk in some sort of form. Now, let me remind you, for binary outcomes, the notion of calibration that we looked at was that the probability of a success given the predicted probability should be the predicted probability. And you can show, it's not completely trivial, but it is in the literature, that for binary outcomes, and only for binary outcomes, these two notions of calibration coincide, which is very nice, right? You have to randomize, of course, a bit for the binary outcomes, but when you do that properly, then probabilistic calibration, or this notion of calibration for binary outcomes, is exactly the same. Now, that's no longer true when we have real-valued outcomes. Now, sorry. But let me quickly, before I move to this, let me quickly give you, sorry, I put in something here that I forgot about. Let me briefly argue why we look at these pit values. I guess it should be clear to many, but let me just for completeness review it. We know that if we have a random variable with a deterministic continuous CDF, then g of x has a standard uniform distribution if and only if x has distribution g. That's what you show in one of the introductory probability classes. Without continuity, you can show something very similar, and that's this here. So the probability that g of x is less than alpha, is less or equal to alpha, and this is less or equal to alpha, then the probability of, here we take the left continuous version of the CDF, that's less or equal to alpha. This condition holds for all alpha. If our g is continuous, this simplifies to that. But if it's not, then it's enough to have this equivalence here to x having distribution g. And that also gives you a hint on how you should randomize when you have jumps in the CDF G. Okay? So this just tells you also here we're approximately uniform, right? As uniform as we can get with jumps. Second motivation, and that one I find quite interesting. If you have a time series, yt, and you make predictions here, so the only information you use for predictions are your past observed values of y until the time point before. Okay? So then you have that if your prediction ft is the law of yt given the previous points, that happens if and only if the PIT values are IID standard uniform. Okay? Now you may say when you see this, you think that these PIT values are really all we need. The problem is that this is very specific to this situation. It only works in this case. It works only for lag 1 predictions. It's already false if you predict 2 time steps ahead. And it doesn't work anymore if you have more information here. Like when you think about all modern prediction problems, you don't only want to include the past observations of y as your information, right? You want to put other covariates. But as soon as you put other covariates, this equivalence breaks. Okay, and you see this here. So here we go back to the pictures. Now I put here how we generated the observations. So y is standard, mu is standard normal, and y is normal with mean mu and a small variance. The small variance is just that the pictures look good. This is not important that this is small. Now you see the first one here. This issues the correct conditional distributions, and we get probabilistic calibration. That's nice. Now the second one is the disconcerting one. This one's also probabilistically calibrated. You also get, if you plug y into f, you also get a standard uniform distribution. The third one with the sign flip, comforting enough, that's not probabilistically calibrated. The last one is the marginal distribution of y that's predicted here. That's obviously uninformative but calibrated, so there, that's also not surprising. Just reminds us that calibration is not the whole story because we also want our predictions to be informative. Okay, so why does this second one happen? Here, this is a very busy slide with a lot of formulas. Let me walk you through it. I don't expect you to take in all of them. I just want to give you an overview of the many notions of calibration that make sense for real-valued outcomes. So focus first here on the bottom. Here we have probabilistic calibration that I have discussed before now. Here that's the case for the continuous outcomes, and here in gray you see this notion that you can define if you have possible jumps. Now then go maybe all the way to the top. Here you see what is called auto-calibration. So you would request that the conditional law of y, given the prediction, is the prediction. So that's now very, very analogous to the binary case. We wanted that the probability of success, given the predicted probability, is the predicted probability. Here we do essentially the same thing. We say that the law of y, given our random predicted CDF, should be that random predicted CDF. That's auto-calibration. Now, in the binary case, this one and this one coincide. In the real-valued case, they're far from each other. This one is a much more stringent condition and much more restrictive. Now, This is something in between that here we don't have to focus on too much. Then auto-calibration implies threshold calibration. What does threshold calibration mean? Threshold calibration is one way of going back to calibration of binary predictions for real-valued ones. So you look at every binary event that y exceeds a certain threshold little y, and you condition on the predicted probability for this, and then this should be this predicted probability. And you do that for every threshold. Very sensible thing that you think that this should hold. Auto-calibration also implies quantile calibration, that's this here. So there you say that if I look at the conditional quantile of y, given the predicted quantile of y that I have, that should be the predicted quantile. So that's also something that follows from auto-calibration, and quantile calibration is a little bit stronger than probabilistic calibration. And here from threshold calibration, you can marginalize over all thresholds, and you get to something that's called marginal calibration. So that means that if you take the marginal CDF of your y, that should be the same as the expected CDF that you are predicting. Okay? So here you see there's quite a bit more when you look at real-valued outcomes, and our target should really be auto-calibration. Now, this zoo of calibration notions gets even worse when you focus on the tails, but also for tail probabilities, there is now notions for calibration. Now let me go back to this picture. Maybe we can make more sense of this now. The first one here satisfies everything we want. It's auto-calibrated, it's probabilistically calibrated, it's marginally calibrated. Now the second one we can identify, it's not marginally calibrated. So if we look at the marginal probability of the marginal distribution of y, that's not the same as the expected forecast that we issue. So that fails here, and hence it cannot be auto-calibrated either. Now, this one should be a warning that concepts that look intuitive for calibration, you really have to understand them in order to draw conclusions. You see that the predictions are far from the observations, but this one is nevertheless marginally calibrated, because the sign flip is such that things nicely average out. So it's just a word of warning, like here, this was the word of warning about probabilistic calibration. Here, that's the word of warning about marginal calibration. Of course, they look convincing, and of course, they're very good properties because they're necessary conditions for auto-calibration, but they can have flaws. The last one is, has all good properties, it's just uninformative. Okay, so I tried to argue that probabilistic predictions should be calibrated. Ideally, they should be auto-calibrated. And I would add that subject to calibration, they should be sharp in order to be informative. What do I mean by sharp? I'm purposefully vague here a bit about what sharp means. Sharp, if you think of normal predictive distributions, they should have a small variance, right? You should have short prediction intervals. But sharpness can mean a bit different things in different contexts. But anyway, you want them to be informative. Now, if we want to compare probabilistic predictions, we should do so with proper scoring rules. And I will say about that a bit more in a moment. Those proper scoring rules assess calibration and sharpness simultaneously in a certain way. And I'll try to give you a few hints on why they do that and how they do that. Before, I have two small comments still on calibration. What about multivariate outcomes? Suppose you have y is equal to RD. Now the forecast is a distribution over all of RD. Auto-calibration is still an applicable tool. It's still, the definition is just the same for multivariate predictions. But yes, things don't become easier when you work with multivariate predictive distributions. So typically, what's checked in applications are graphical tools similar to pit histograms, where the d-dimensional distributions are just somehow, you have a dimension reduction function that brings you down to dimension 1, and then you check if corresponding one-dimensional distributions have been predicted in a calibrated way. We will have at least one talk about such ideas in this conference, so I will leave it at that. The main use tool, I would say, are multivariate rank histograms. Those are specifically for multivariate predictive distributions that are issued as ensembles, so as discrete distributions or distributions with a finite support. Okay. Now one last comment, it's more a word of warning. I'll keep it short, but I think it's not always universally known, and it's a very sad story in some sense. It's something that bothers me, and I think I don't have any good solution to it, but I think it's something one should be aware of. Calibration and averaging don't go well together. Averaging is something that typically always is good and makes your life easy and is a great thing. With calibration, unfortunately, it's not. So if you have two calibrated predictions for y, then in a very general sense, if you take their average, it will not be calibrated. And that's not a statement of maybe you're unlucky, it's not calibrated. You can actually provably show that it will never be. So here's a more one example of a rigorous statement, but there's many types of these statements. Suppose you have two probabilistically calibrated predictions for y, and you take now any convex combination of them, then this convex combination will have a variance that's smaller than 1/12, which is the variance of a standard uniform. So you cannot be standard uniform. Okay, so taking convex combinations of calibrated predictions destroys calibration, and not sometimes always. Of course, if you start out with predictions that are not calibrated, then you may improve calibration by convex combination. But if you know you calibrated before, then don't average. Okay, there's more than this literature. This result is here in this paper, but it has been noted in many different cases. Okay, so this brings me to the end of my calibration part, and I would move on to proper scoring rules, but are there questions at this point that I'm also happy to take them at the end. Okay, so proper scoring rules. What do I want to talk about? I'll give the definition. I'll say briefly how you compare forecasts with proper scoring rules. I want to talk a little bit about how proper scoring rules behave with regard to different information sets. Proper scoring rule decompositions, that shows somehow the connection between proper scoring rules and how calibration comes into play. And briefly, I'll talk about one severe limitation of proper scoring rules. So what is a proper scoring rule? We have P is a class of distributions on our outcome space Y. Now here this is a class of distributions. There's nothing random about these distributions. And a scoring rule is a function that takes in as an argument a distribution and an outcome. And we want it to be, I just wrote suitably integrable. I didn't want to put too many technicalities. All the expectations we have here should exist or be finite, whatever we need in the appropriate place. Now then we say that a scoring rule is proper if you take the expected, so if y has distribution f, that's what I symbolize here by this expectation with a lowercase f, the only thing random in this expression here is y, right? F is a deterministic CDF here. So the expectation of the scoring rule when I plug in f should be smaller than the expectation of the scoring rule when I have any other prediction. Okay, so the true distribution of y as a prediction should minimize the expected score. And we speak of strict propriety if equality in this inequality implies that f is equal to g. So I guess that's fairly natural concept. Now these scoring rules, they are interpreted as penalties, right? So lower scores are better. Argue that should be called loss functions, but they're called scoring rules now, so I don't think we can do anything about this. Some pieces of literature orient them the other way, but for the majority, they're oriented as penalties. Forecasts should be compared with proper scoring rules. So probabilistic forecasts should be compared with proper scoring rules. There's very good arguments for it. I'll try to give you some of them now. I will also try to make more sense of the phrase that proper scoring rules evaluate sharpness and calibration simultaneously. They're also increasingly important in estimation. And here, just if you're interested in proper scoring rules, tiny bit of advertisement on my own cause. We have a new review article on proper scoring rules out So do check it out if you're interested in proper scoring rules. Okay, so here are two examples for the binary case. So here we have our curly Y is now again the case of binary predictions. Two very popular proper scoring rules are the Breyer score, that is just the squared error between the prediction and the between the outcome and the predicted probability. And the other one is the logarithmic score, which is essentially just the negative logarithm of the density of Y, of the predicted density of Y at the outcome. Okay, so this is for the binary case. These are two prominent examples. There's more. There's characterization results for all proper scoring rules. In the case of binary, yes?
Yes, I'm just curious, in the Breyer score,
Yeah.
is there a reason for the squaring operation, or could it be any sort of well-behaved convex? Could I use the absolute value instead of squaring, or could I take the difference to the power of 4 and still get
And still get propriety.
Sorry?
And still get propriety.
Yeah, and still get something that's well-behaved and meaningful. Just wondering if the squaring itself is magical or canonical. It's just a choice.
I don't think you can take anything. No. No, you will lose propriety.
Okay.
You have to be careful what you take. Yeah. It depends a bit what your goal is. For forecast evaluation, if you really want propriety the way we stated there, I think you are tied to the square.
Okay.
But yeah.
Thanks.
But yeah, it's a bit more. In some cases for estimation, you can take anything convex. But if you go for forecast evaluation, no. No. Okay, so how do you compare forecasts with proper scoring rules? Well, you pick your favorite proper scoring rule, and then you compare average realized scores. So for this, you need a sample of two competing forecasters and observations, and you compute these average realized scores. And then you say that the forecast with the smaller value Sj hat is better. That is what's done when you evaluate forecasts with respect to proper scoring rules. Of course, a lot of questions arise from this. This seems like a very simplistic recipe. And of course, if you have IID forecast cases, maybe you're still somewhat convinced. But then you say, of course, my F is also random. So I do agree with you. This is per se not directly well motivated. And I'll try to motivate it a bit better in the coming slides. It's still the most common thing that's done. And many times it can be justified just by the tower property, but there's also slightly different approaches. And these slightly different approaches come a bit, you have formal tests for whether the difference between two such average realized scores is significant. Classical ones are here the Diebold-Mariano test or the work of Giacomini and White. In sequential settings, slightly different comparison proposals have been made. So this is more recent references. But fundamentally, you're comparing average scores of some sort. Okay, so this is what you would do for forecast comparison. So let me get, here's the simulation example we had for the binary case, just that you see here what this looks like. These were these different forecasters. And here, this is the prediction, and here we have the two scores I showed you, either the Breyer score or the logarithmic score. And you see that P3, that was our most informative forecaster, gets under both scoring rules, gets the best score, and then just the way the ordering we expected, they get worse and worse scores. So this seems comforting. But one can, of course, ask the question, does forecast comparison depend on the choice of the proper scoring rule S? And generally, the answer is yes. The only guarantee we have with a proper scoring rule is that it will incentivize and give preference to the best forecaster, to the one that predicts the correct distribution or conditional distribution, depending on our setting and how we evaluate. But of course, things can go wrong. One example can be finite samples, that you simply don't approximate the expectation well enough. But also under non-nested information sets, if you have uncalibrated predictions, different proper scoring rules will give different preference to different forecasters. And that even holds on the population level. It's not so surprising to think about this, right? We have one optimum, let's say we have a fixed information set X. We know we have the conditional law of Y given X as our optimum. And now the proper scoring rule, we know in expectation gives preference to this one forecaster. But then how, when you go away from the optimum, how does the expected score behave in the space of probability distributions when you go away from the optimum? That depends on the proper scoring rule, right? And one may go away like this. So a violation in this direction is not penalized as much as in this direction. And another one may do the opposite. And then, of course, you get different rankings when you do evaluation with respect to different scoring rules. Now, you can, of course, ask, can you avoid the choice of a proper scoring rule? And then the answer here, it comes into play that binary outcomes are also predictions for the mean. In that case, you can. There is some work in this direction for binary outcomes. Sometimes you can avoid and evaluate with respect to all proper scoring rules simultaneously with so-called Murphy diagrams. In the general case, no, you have no chance. You do have to make a choice on which proper scoring rule, and different ones will give you different rankings. Now here are two examples for the real line. One is the logarithmic score. So suppose you have density forecasts, then you take minus the logarithm of the density evaluated at your observation. That's, of course, very well known to everyone from maximum likelihood estimation. That is at the heart of maximum likelihood estimation. That's also not a novelty. It's just one example of a proper scoring rule. Another one that's very, very popular is the CRPS, the continuous ranked probability score, which has very broad generalizations in terms of kernel scores and so forth. But this is here the most prominent member. It has one big advantage now in comparison to the log score. You can compare here, you only need that F has finite mean, so you can compare predictions for Y that are given either as densities or as discrete predictive CDFs with the same loss, which you could not do with the log score. The log score has other advantages. I don't want to argue for one or the other, but just one. You may ask, why do I even need something else than the log score? And that is one of the reasons. And this CRPS has also been increasingly used in estimation, also as a training objective in many machine learning models. So there's a lot of work going on also trying to understand why this works well. But that's there's lots of new stuff still coming out of this. Okay, now I will try to give you two ideas of why we should evaluate proper scoring rules, use proper scoring rules to evaluate predictions. One is about information sets. So suppose our F is what we want. It's the conditional law of Y given X. And G is some other forecast that's also based on X, right? Doesn't use any other information than X, but it's maybe not optimal. Then we know, and now here F and Y are random. Then we know that the expected score of F will always be less or equal than the expected score of G. Okay, so in that sense, that's comforting. If F is better and G does anything else with the information, then we will prefer F over G. Another corollary to this is if F is optimal based on information, on more information than G, then F will be preferred over G. And we will have equality here if and only if here Y and Z are conditionally independent given X. So you have equality only if the extra information that forecaster F uses is actually useless to predict Y. Okay, so that's another reason why proper scoring rules are a good idea for evaluating probabilistic predictions. Okay, now let me come somehow to my final part, scoring rules and calibration. How do proper scoring rules and calibration connect? So the goal is here, can we somehow decompose our average realized score, that was this object that we used to compare our predictions, into interpretable terms that quantify how calibrated the forecast is, so a miscalibration term, a discrimination ability term, that's the term that would quantify how informative is our forecast, and an uncertainty term. And the idea is the following. You can write the expectation of the score as, this is a miscalibration term, so we have the expectation of the score minus the expectation of the score if we plug in the best, so the best auto-calibrated forecast given the information that we have in our forecast. Right, so if you look at this, the law of y given f, that's the best auto-calibrated forecast we can give if f is our information. So the difference between what we've issued minus this calibrated one, that should tell us how miscalibrated we were. Now, discrimination ability here is specified as what is the score if we predicted the marginal distribution of y. So we make this prediction of, that I said we predict the marginal distribution of temperature over the year for tomorrow here in Cambridge. That would be this prediction. Now the question is, how much more do we discriminate if we use our information optimally? So that would be our discrimination ability. And then the uncertainty term just means how hard is our prediction problem. So that would be, it would be nice if we can compute such components of a score, if we can decompose, of course, such a realized average score akin to such a theoretical decomposition, then we could somehow give meaning to why is one method preferred over the other. We can say it's better in terms of average score, and we can say how much is due to better calibration and how much is due to better discrimination. Okay? Now, how do we empirically translate this idea? Well, for the uncertainty part, it's relatively easy. We plug in the marginal distribution of y as our estimate of the true marginal distribution of y. And then for the miscalibration term, it's given here. We somehow need an estimate of this conditional law of y given the forecast distribution. And we need it that it's in-sample auto-calibrated, because otherwise we don't get a miscalibration term that's positive. And that's kind of strange. We cannot interpret negative miscalibration. Now, generally, it's not feasible in that generality. It's just not possible. It degenerates. But there is one way out that we've recently proposed. If S is the CRPS, so this is specific now to the CRPS, doesn't work for any proper scoring rule, then you can get a possible solution using isotonic distributional regression, and you can actually estimate all these different terms of such a scoring rule decomposition. And the discrimination term is then just estimated by the remainder. Okay, I just want to give you pictures on what this looks like. What additional evaluation possibilities does that give you? What have we compared here? These are, maybe you know them, these are benchmark data sets in machine learning. And there's a model that gives point predictions in these benchmark data sets. And then the comparison is between different uncertainty quantification methods. So methods that from some model generate you predictive distributions instead of best guesses. And the question is, which of these uncertainty quantification methods does this most skillfully? Now, these diagonal lines are, these are level sets of the CRPS, right? So here it gets smaller, so your best point, the best method would be in this upper corner. Here the average CRPS would be 1.2, and then it goes down here to 2, okay? Down here we have miscalibration. So the further a method comes on this end, the better it's calibrated. And here's discrimination ability. So the higher a method on this end, the better it discriminates. And what you see here, for example, MC dropout has a pretty good CRPS. It's in fact the best of all the methods here, but it's not very well calibrated, but you see that it discriminates very well. And then here, for example, you have the smooth easy UQ. That's on the other extreme. It's very well calibrated, but doesn't discriminate very well. So they can be very similar in CRPS, but have very different defects that you would not see if you just look at this one number. And that kind of helps you a bit to, I think it's a very nice way to connect prediction ability to the concept of calibration. And of course here, this is just for the other two data sets. Okay, with this I come to the last thing I wanted to mention about proper scoring rules. Proper scoring rules and extremes. I mean extremes in the sense of EVT, in the sense of extreme value theory, really extremes in the sense of looking very far out in the tail of your distributions. Then there is an impossibility result. First, overall, this is due to also work by Torres. You have to be very careful when you evaluate forecasts with respect to extremes. One thing you should not do is you should not condition on the outcome being extreme when you do your evaluation. It leads to skewed results because when you do that, when in evaluation you condition on the outcome being extreme, then typically the optimal forecast would be to always predict an extreme event, because then you're safe. When you condition on the outcome being extreme, your forecast was that you would be extreme, because you've always predicted that. And you're not evaluating when the outcome's not extreme, so that all the other predictions are rubbish. That doesn't harm you in that evaluation. So therefore, you have to be careful. That's what they term the forecaster's dilemma. You have to be very careful not to run into that when evaluating extremes. When you want to evaluate extremes with proper scoring rules, you also have to be careful because they're not directly useful. Because expected scores shown they cannot distinguish between tail probabilities, between tail properties, different tail behavior of predictive distributions. What does that mean a bit more precisely? Suppose you have two different forecasters that have different, they're not tail equivalent, then you can always get them arbitrarily close in terms of a proper scoring rule. Or at least you can always find a forecaster with a different tail behavior that's arbitrarily close to the forecaster that you have. So they don't distinguish different tail behavior. What you can do that we have looked at recently is you can evaluate probabilistic predictions with regards to tails when you focus on calibration. That's then, of course, absolute evaluation. It's not comparative. There's no proper scoring rule. But there are notions of calibration with regards to tails that you could resort to as a first thing. I want to emphasize this is really about extremes in the sense of extreme value theory, in the sense of really letting the threshold go to plus infinity. When you're just interested in high impact events or high events, events that happen beyond a large threshold, then there's a lot of tools from proper scoring rules that are very adapted to this, and we will also have a talk about this. So in those cases, proper scoring rules are still very useful. Okay, with this, I would like to come to the end. So I have tried to explain that probabilistic predictions should be calibrated in sharp. Ideally, probabilistic predictions should be auto-calibrated, and proper scoring rules allow to compare probabilistic predictions simultaneously with respect to calibration and sharpness, but one should also be aware that the evaluation and the ranking of methods does depend on the proper scoring rule that is chosen. And then I have a bunch of references for you. I think slides will probably be shared in some sort of form, so I don't expect you to look at all these now. So thank you very much for your attention.
Thank you very much. Do we have questions or comments? Yes.
If, from the definition you've given for calibration proper scoring rules, if your predicted distribution, we call it G, is, for example, sampled using an MCMC algorithm, we can use still this definition, calibration, and proper scoring rules, or something changes. So it has to be explicit in order, most explicit possible, the predicted distribution. Or explicit has to be given in practice? Or
well, it can be given. I mean, what's very common is that it's given in weather forecasting. It would be called an ensemble. So it's given as like the empirical distribution of 50 realizations from your predictive distribution, right? That would be very similar. And then you can apply exactly the same arguments.
Okay, so that's I know. And if we
it from an NCMC, then I can take the implicate distribution for that and using it anyway.
I wouldn't see why you cannot. Yeah. Thank you.
Thank you for the talk. You said you were very vague about this idea of sharpness, and I was wondering if you can maybe, give some more detail about how could we maybe quantify it in terms of, I don't know, maybe information theory approaches, or I don't know.
Yeah, I mean, I think there's just many options to quantify it. I mean, one option is what I showed here in the here. This is, of course, one option how you could say you are sharp, right, if you are discriminative. But I also agree with you, you could say you want a small entropy. That is also a valid goal. So if you say proper scoring rules quantify calibration and sharpness, then I guess the way you can make sense of it best is by defining sharpness this way. Whether that's the way that makes most sense to you, I don't know. But yeah.
We have a question in the back.
Thank you for the last presentation. So, looking at this decomposition, I was wondering if you forecast this point forecast and your score is the mean squared error. So there is the bias variance decomposition of the mean squared error. So is there any link with this decomposition?
It's a very nice question. No, there's no direct link. There is a different bias variance decomposition also for proper scoring rules that I have not presented. So there is an analog to the bias variance decomposition of the mean squared error for point predictions, but it's not this one. It's a different type of decomposition.
So we cannot talk about any trade-off here. So with bias variance decomposition, you have the bias variance and the North term. So you can talk about these trade-offs. So here, the examples you gave, you say some of them were discriminative, some of them were. So can we talk about any trade-off?
Not really, no.
No.
I wouldn't. I mean, you kind of want to. You want this to be large. You want this to be small, but there's not a trade-off. I mean, let's say it's hard to speak of a trade-off when you talk about an evaluation method, right? And here I'm talking about an evaluation method, right? You kind of have to have an optimization objective to get into a trade-off. Here I'm considering forecasts as given and outcomes, and I can't do anything with them. I just want to point out this one's good in that aspect, this one's good in this aspect, right? As soon as you go to the fact, I have a method and now I want to optimize it for those two criteria, then oftentimes maybe they will become competing, yes?
Yeah, so if I have f and f prime, I have f and f prime,
yeah,
and I decompose this expected score for this f and f prime.
Yeah.
Can I say that by going from f to f prime, I made a trade-off in terms of MCB and DSC? So that was more the question, because essentially I can use this decomposition to drive or to design new models, possibly, like.
Yeah. I would think that you do get trade-offs sometimes. I mean, one thing that here, I mean, generally, I think if you have good discrimination ability and you're not calibrated, I think you have chances to improve calibration, right? Because the discrimination ability is somehow about information that you have. If you're well calibrated but your discrimination ability is low, I don't think with the forecast itself you can do anything. I mean, it's calibrated, but I don't think you can just increase the discrimination ability, because that would mean you would have to inject information. So I hope that kind of makes sense.
Thank you very much.
Yeah.
Yes, I think you're first.
So I have one question. I might have missed something because I was reading the paper about
Okay.
But, so my question is, you seems to use as proper scoring rule the expected calibration error, and would have used that to say to what point a model is well calibrated. So why not considering the expected calibration error that could be a scoring rule? I think no.
So what is the expected calibration error?
It's a kind of you kind of measure the difference between the difference between the integral the diagonal curve that you have on your reality plot versus the kind of calibration plot. It's to.
But you can only do that for binary events, right? You don't have any such plot for real valued outcomes.
So you can do it with for binary classification or multivariate classification, yes. And you can also use it for regression. There are also definitions for regression.
Okay. Well, it would be interesting maybe to see what the relationships are. Yeah.
Okay. I was okay.
That would be nice to discuss if there is a relationship and what it would look like. Yeah.
And then we have one more question.
Yeah, thank you for the talk. In the probabilistic identification, people have been decomposing the expected proper scoring rule using the isotonic regression algorithm. But in the end, we have two terms, a calibration term, which is the minimum expected proper scoring rule, and the discrimination term. And I was not aware with this concept of auto-calibration, so do you have any intuition or link between this calibration term with respect to the auto-calibration and the calibration term that is given by the isotonic regression?
Well, I guess for the isotonic regression one, you would have that would be for point predictions, right? It's not for the CRPS. It's not for a proper scoring rule, right?
It's for binary. It's for binary proper scoring rule.
For binary, I agree. So essentially, I mean, it's a very good point. I didn't go into detail here. Essentially, we've just no, that was too far. We've just generalized this isotonic idea to the distributional case. What you see here, it comes in, you use isotonic distributional regression. But I didn't introduce isotonic distributional regression here. But it's fundamentally the same thing.
Okay.
It's just a generalization of this binary case to the distributional case.
Okay, thank you.
Yeah.
Perfect. All right, let's thank Johanna again, and then we're having coffee.